All right, everybody. So let's go ahead and get started with today. Oh, yes. A stapler. Yes, I do. At least I should, unless someone stole it. Wait, where's my stapler? What? No. Oh, it's shoot. I don't. Sorry. On that front. So as a college student, highly recommend this thing called a Swingline Topped. It's a little baby stapler. It's like this big. You can put it in your backpack, super easy to have. You become everybody's best friend when it comes to solving something. Okay. So let me go ahead and turn off the light here. I think it's okay. All right. So we left off with this one. We didn't get to finish it, but like notice that part A, B, and C, they kind of set the stage for you. They said, like, first find the left-hand right and right-hand limits, and then declare whether or not the limit as x approaches -1. What if the question just asked find the limit as x approaches 2, where 2 is a dividing value? That's a situation where you have to check the left and the right-hand limits to see if they agree. If they agree, then the limit does exist. If they don't agree, then you know the limit does not exist. So we need to check left hand and right hand limits. So the limit as x approaches 2 from the right of f of x is equal to. All right, so looking at the function, because I don't have that. If you're approaching from the right, which function are you going to be? 1, 2, or 3? 3, because your numbers are going to be larger than 2. So you're going to be greater than 2. So on the right-hand side, the limit as x approaches 2 of f of x becomes the limit as x approaches 2 from the right of 2 minus 1/2 x squared. Right? Or no, 1/2 x, excuse me. So that has no issues, right? Dividing, like you're not dividing by 0 or anything like that. So you can just plug in the number. You get 2 minus 1, which is 1. So 2 minus 1/2 times 2, which is just 1. The limit as x approaches 2 from the left of f of x. This time, since you're approaching x from the left, or 2 from the left, you're talking about values that are less than 2, which means you're in piece 2 of your function. Meaning, what I mean by that is that when you are approaching 2 from the left, your function is going to be the middle function. So this becomes the limit as x approaches 2 from the left of x squared minus 3, which equals 2 squared minus 3, that's going to equal 1. These agree. So the limit does exist. Thus, limit x approaches 2 of f of x exists and equals 1. I'm just being pedantic there. If you want to just say the limit as x approaches 2 equals 1, that by definition, like by statement, means that the limit exists, right? If you say the limit equals 1, you're saying that it exists. But I want to be very, very particular and just mention the reason it exists is because the left and the right hand limits both existed and both equaled the same number. Any questions on that? So when it comes to piecewise functions, we need to be careful when we're finding the limits at dividing values. If you're approaching a limit on an individual piece, like if I was to ask you to find the limit as x approaches 0, then you don't need to check the left and the right hand limits. You can just go straight to the function here. In fact, I probably should make that an extra question. Say the limit as x approaches 0 or the limit as x approaches -5, something like that. I'm going to make a comment to myself to do that. Actually, that's a really fun way to think. Okay. Apologies. I just decided I want to make that a fun question to add to it. Okay, so that covers all of 1.3. So 1.3 was talking about one-sided limits. Now, the reason why we needed to do those is particularly to deal with 1.4, which is limits involving infinity. So there's two different types. There's infinite limits, and then there's going to be limits at infinity. So notation, if the value of the function increases or decreases indefinitely as x approaches a, for some constant, then we say that positive infinity or a negative infinity is the limit of x as x approaches a. Mathematically, we write the limits as x approaches a of f of x equals positive infinity or negative infinity, depending on the case. Now, that's what we'll write. Now, because I'm assuming there's going to be a sleeper UNLV math teacher, it's going to say, aha, Phil, you said that an infinity isn't a number. So how can a limit equal infinity? It doesn't, right? Infinity is not a number. This is just, so the note here is that one, even though, not even though, the limit doesn't exist, we just know more about it. So if it were to approach positive infinity, that's not a number. So the limit doesn't converge, but it does tell us more about the limit. So sometimes limits just don't straight up exist because they oscillate back and forth, and like we saw on the first lecture day of unit 1.1 with sine of 1 over x, right? Because it just kept bouncing back and forth, and you couldn't determine the value. Sometimes that happens. Sometimes it means that the left and the right hand limits don't agree, like we saw with piecewise functions. But every once in a while, when you find a limit, it keeps increasing definitely or decreasing indefinitely. And so even though the limit doesn't exist, we know more about it. We can say that it's tending towards positive or negative infinity. So yes, it's not actually a limit, but it is necessary to mention because it tells us more about it. It gives us more information. Is that okay? I don't know why I wrote notes. It should just be note. Oh well. Typo. So find the that's right. That's the other one. 2. I remember now. If we get number over 0, the limit will be either positive infinity, negative infinity, or DNE. And we'll see that with this with these two examples. So there is a very, very formal way to figure out whether it's positive infinity, negative infinity, or plus or minus, or DNE. And that's kind of really nasty. There's a better way. There's an easier way. And that's going to be having to do with plugging in numbers close to it to figure out what sign you're going to get. So let's go ahead and start with part A. The limits as x approaches 1 from the right of 1 over x minus 1 squared. As with any limit, we should always try and plug in the number and see what we get. But of course, you're going to see we get 1 over 0. Oh, no. Exactly. Oh, no, it fall. It does not work. And so, but this is not 0 over 0 because there's no polynomial. Well, I mean, it's technically a polynomial. It's 1. It's technically a polynomial. But there's no variables in the numerator, so we can't cancel any factors. So how do we approach what this thing is going to be? Well, we know, like just imagine if you were to divide by 0.001, right? If you divide by 0.001, you get a very large number. And so I found my calculator. And apparently my wife just texted me saying that she found the comb. So I found my comb again, but I don't know where. I don't know where it was. But 1 divided by 0.000001, right? You're going to get 1 billion, right? If you add an extra 0, you get 1 you get 1 to the 10 to the 10th, or 1 times 10 to the 10th. So you get 10 billion. And if you keep adding extra zeros, if you keep getting closer and closer and closer to zero, it will just keep getting bigger and bigger and bigger. So that's going to be our trick. So if you want to know the formal way, what you would say, like this is the formal way. As x approaches 1 from the right, 1 or x minus 1 squared will approach what? So if you plug in 1, you're going to get 0 squared, but it's from the right, right? You're going to get 0 from the right. Is that correct? Right, because 1 from the right, like 1.1, 1.01. So 1.1 minus 1 is 0.1. That's a positive number. So it's going to 0 from the right-hand side. So 1 over x minus 1 squared is going to approach 1 over 0 plus, which will approach positive infinity. If you divide 1 by basically a tiny speck that's positive, it will become infinity. Like as you keep getting closer and closer to 0, the number is just going to keep getting bigger and bigger and bigger and bigger, but it's a positive 0. So it's going to be infinity. That's the formal way. The informal way, and the way that I would like you guys to do it, is to test like the quote unquote better way. Test a value to determine sign. Then choose positive infinity or negative infinity accordingly. So if you get, when you plug in a number, like when you do a test value, if the number you get at the end is positive, it's probably going to be a very, very positive big number. Say that it's going to be positive infinity. If you get a negative number, it means it's going to go to negative infinity. And that's only with the one-sided limits. With regular limits, then you have to check the left and the right-hand sides, unfortunately. Because, and you'll see it in a picture in a second, of why that is the case. So what we'll check, so for ours, try x equals 1.1. Let's just do 1.01. Usually enough to do just 0.01. You can do more if you want, but then let's do that. So 1 divided by, in parentheses, and just so we're clear, so we're all in calculus, so we probably have a little bit of experience with the calculator, but just in case you did not know, the calculator is only as smart as you make it. It follows PEMDAS to a T. It follows the order of operations to a T. So if you plug into the calculator, if you do this, 1 divided by 1.01 minus 1 squared, it reads this purely based on PEMDAS. So it says, okay, take care of the exponent first. So it just squares the 1 because it doesn't see any parentheses. And then when it does, it goes to division. So it does 1 divided by 1.1 and then minus 1. It doesn't do it right. So when you're doing these things, either use the function or calculator to make this into a fraction, or make sure you put this in parentheses so that it follows the proper order of operations. Your numerator should be in parentheses. Your denominator should be in parentheses. Otherwise, it will not get you the right answer. Is that clear? All right. So if I do this, 1 divided by 1.01 minus 1 squared, I get 10,000. We get 1 over 1.1 or 1.01 minus 1 squared, which is 10,000. That's positive. So that implies positive infinity. Does anybody have any questions on that? That's how we're going to do it. So we're going to kind of do a combination of the formal way, which is looking purely at it as a concept of 0 plus, 0 minus, and so on and so forth. And then from there, determining things. But the more intuitive way would be saying, okay, so it's going to be dividing by 0, which means it's going to be dividing by a very, very small number as we get closer and closer. And so what are the y values tending towards? Let's just plug in a number. We know that it's going to either blow up towards positive infinity or negative infinity. So whatever number we get, if it's positive, the answer is going to be positive infinity. If it's negative, the answer is going to be negative infinity. So let's see that in action on part B. So part B, you get the limit as x approaches 1 from the left of 1 over x minus 1 squared. And so we already know it's going to be 0 over, it's going to be 1 over 0, so we don't need to try it again. So we're going to try x equals 0.99. Try 0.99. You could try 0.999 if you want to. Doesn't matter. But try 9.9. You get 1 over 0.99 minus 1 squared, which ends up being, if you plug it, and this is why I love having this calculator, by the way. Don't re-enter it. You can press the back button and it brings you up into the screen. So you can just change the number by deleting the number. Just delete, 0.099, or not 0.99, 0.99. And lo and behold, I get 10,000 again, which is positive. So the answer is also positive infinity. And that is because it was squared, right? Well, x minus 1 would approach 0 negative. Let me write that down. You don't need to write this down. But x minus 1 would approach 0 from the left-hand side. But when you square it, it becomes positive. Because it's going to be like 0.01, negative 0.01 squared, and that becomes positive. So because it's squared, they both go to positive infinity. So what do we know about the actual limit, C? The limit goes to positive infinity because the left and the right-hand limits, quote unquote, agree. So like, yes, they don't agree because it's not actually a limit. Yes, blah, 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 but they both go to infinity. So for the actual limit will go to infinity. Since A and B went to positive infinity, the limit as x approaches 1 of 1 over 1 minus x minus 1, excuse me. X minus 1 squared is also equal to positive infinity. And you don't need to write the plus sign, by the way. Did I mention why I do that? Yeah, I got marked down. And this was a class where it was based on a curve, which, trust me, you never want a curve. You never want a curve in a class, because if everyone does really, really well, then it means that only 1 point difference means difference between an A and a B, which happened in this classroom. So that's why I was really, really upset, because I got 1 point off, and that meant the difference between like an A and a B plus, and it's just really upsetting. Because I scored basically an A if you're looking at it purely in standards, but based on the curve, I got a B. I don't like curves. Curves are no fun. Okay.
Since A and B is sine.
Since A and B went to positive infinity, the limit will actually go to positive infinity.
Okay.
Now it's going to be different when we look at 1 over x minus 1 to the first power. Same thing would happen if that was to the third power, by the way, but let's check this one out. Now it's going to be less space. So A, the limit as x approaches 1 from the right of 1 over x minus 1. You'll try plugging in 1. You'll see that you get 1 over 0. So we're going to try x equals 1.01. And what you'll get is you'll get 1 over 1.01 minus 1, which ends up being 1 divided by 1.01 minus 1. You get 100, which is positive. So the answer is that it's positive infinity. So the limit as you approach it from the right is positive infinity. However, if you approach it from the left, the limit as x approaches 1 from the left-hand side of 1 over x minus 1, we'll try x equals 0.99, and you get 1 over 0.99 minus 1, which will equal negative 100. So that's negative. So the answer is going to be negative infinity for the second limit. So as you approach it on the left, it goes to negative infinity. Yes?
No, it's squared, right?
Yes, it's not squared. Part B is not squared. Or example 1.4.2 is not squared. And that's just as a good reminder about this fact is that, what's the word? When you square something and raise it to an even power, it makes it positive, right? So we need to be wary of that. Julie, you had a question?
Do those numbers stay constant when we're doing the right and the left, the 1.01 and the 0.99?
Yeah, so we're just gonna pick a number, like you can even go, like you can even go ahead and do 1.1 and 0.9. That is sufficient. Because all you're really looking for is just the sign. I just like to get a really, like, I just like to verify it for myself that it's gonna be a big number. But 1.1 or 0.9 would be sufficient. Good question. So you can test it with whatever you want. If you want to go, like, if you want to go bananas and troll me on a quiz or an exam and put like 0.9999999, like write it all the way off the page, you could do that. If you guys remember from 126, you had to draw this, you had to sketch a polynomial. Remember how, like, you would give it a bunch of the factors and you had to draw the polynomial. Do you guys remember that? And so I told my students, like, you're doing a sketch, so it doesn't have to be perfect. So I had students like draw this. And like just make it go out crazy off the page. Thought it was fun. Okay. Part C. The limit as x approaches 1 of 1 over x minus 1 is equal to what? D and E, because the left-hand side went to negative infinity, but the right-hand side went to positive infinity. Because left hand and right hand did not agree. And-
I'm sorry.
No, go ahead.
So all these limits don't exist, but we're just finding if it goes to negative infinity.
Exactly right. So like, because infinity isn't actually a number, like saying that it equals infinity doesn't really make sense. But what it does say is that we know more about the limit. We know more than it just doesn't exist. We know that it is tending towards large numbers. And so that brings up kind of like an application of limits, is like asking, what is the limit of this population model? Is it going to just kind of, does the limit not exist because like the population just keeps fluctuating constantly back and forth randomly? Or is it tending towards infinity? Or is it going to decrease impossibly? So that's what this is all about. More like from a mathematical concept, the use of this, it has to do with asymptotes, but we'll get to that in a second. All right, so we can try to do this one. The first thing we should always try and do is try and plug in the number, right? Let's try t equals 2. You're going to get 4 plus 4. So 4 plus 4 minus 3 is 5 over 4 plus 2 minus 6, that's 0. So unlike with the previous examples where we would factor it and go from there, we don't even need to factor because we're just going to be testing a number. So that's nice. I mean, if you factor it, it might be nicer to plug in the numbers, right? Just because you don't have to do any squaring or anything like that, but it shouldn't be too bad, especially with these calculators and the fact that you'll be able to change it very nicely. So what we're going to do is we're going to try, what number should I try? 1.99 would be good. Try t equals 1.99. And what we'll get is we'll get 1.99 squared plus 2 times 1.99 minus 3 over 1.99 squared plus 1.99 minus 6. Now, by the way, I'm writing this in red. I'm writing this down. If you just try t equals 1.99 and then write down what the number is, that's fine with me. That's sufficient. I don't need you to like show me the calculation. You can plug that into your calculator because you're not doing that calculation by hand. I guarantee it. But let's try that. So 1.99 squared plus 2 times 1.99 minus 3 all over 1.99 squared plus 1.99 minus 6. And you get negative 99, right? Does everyone get the same thing? So I get negative 99, which is a negative. So the answer is that this is equal to negative infinity. So I guarantee you, if you add just an extra point, an extra 9 on the end of those things, it'll go to, I think, negative 999. Add a third one to go to negative 999, negative 9,999, and so on and so forth. That's the same limit here. So we already know that it's going to be 5 over 0 if we plug in 2. So we'll just try t equals 2.01. And just to save on time, so this is why I love having a calculator, because all I need to do now is just go ahead and change all the 1.99s. Delete, 2.01. Delete, 2.01. 2.01 squared, and then you should get 101. Is that what you guys get? Yes. So get 101, which is positive. So this limit will equal positive infinity. And therefore, as a little thought bubble, this is on side note land. This is in your head. Since the left and the right hand limits did not agree, one of them is negative infinity, one is positive infinity. That means that the limit as x approaches 2 from the right hand side, or not x, excuse me, t. That's just a dummy variable. T squared plus 2t minus 3 over t squared plus t minus 6 does not exist. Just as an observation. So let's see here.
Then wouldn't you just write as t approaches 2, or would you write as t approaches 2?
Oh, sorry, not plus. You're absolutely right. Thank you. Leslie caught me. Leslie, right? Yeah. Leslie caught me there. It should not be the limit as t approaches 2 from the right hand side. Limit as t approaches 2. We already found t approaches 2 from the right hand side, and we found that was negative. So, all right. If you guys don't mind, I think we're gonna, well, let me see. Let's try plugging in t equals negative 3. I don't.
399 over 20.
399 over 499.
340. 399.
Okay. Let's plug it in. Let's try. T equals negative 3. You're gonna get 9 plus 6 minus 3. It's 12. Right? And then 9 plus 3 minus. What the heck? Try 3, you get 9 plus 6 minus 3 all over 9 minus 3 minus 6. That's going to be 12 over 0. So we got to plug in values. So let's try t equals. We're approaching negative 3 from the left. So what number should I use? Negative 3.01. I'm going to negative 3.01 or negative 2.99. Which one? Negative 3.01. This is the thing that always trips me up. Believe me, I made this mistake when I was learning this too. So let's think about that one more time. We're approaching from the left. So on the number line, if you're looking at it, and there's no shame in doing this. I still do this sometimes. If we're looking at the left, we're talking about negative 3.001. 3.01. So we're going to try negative 3.01, and you end up with, you should get a positive or maybe a negative number. I don't know. So you get, and this is one thing that's very, very important about your calculator as well. Remember to put the negative numbers in parentheses. Otherwise, it reads the negative number on the outside. So like, we all know the difference between negative 3 squared versus the quantity negative 3 squared, right? One of them will give you negative 9. The other one will give you positive 9. So just make sure you you put your negatives in parentheses if you're squaring. So parenthesis negative 3.01 squared plus 2 times 3 times parenthesis negative 3.01 minus 3 over negative 3.01 squared plus negative 3.01 minus 6, and I get 0.8 something. Is that right? If you put in the, okay, so you get 0.80039 da 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 da. Okay, so that doesn't that's a positive number, so I would be led to believe that it should be positive infinity, but that seems like a small number. Every single other time we were getting big numbers, you can like 100, 200, 1,000, 10,000, so on and so forth. So I'm going to add an extra zero. I'm going to do negative 3.001 just to be safe. Never hurts to be safe. Oh, what am I doing wrong, guys? Where did I make a mistake? Where did I make a mistake in my calculation in blue? T equals negative 3. Sorry, what's the name?
Maybe, so you did 9 of
6
6 instead of
9 minus 6. So there's the issue there. So I'm all messed up. So I'm so sorry about that. We get 0 over 0.
Oh,
So you don't need to test the one-sided limit thing. You don't need to test the values. This is 1.3 stuff. So we'll just factor it and do it the normal way. So limit as t approaches negative 3 from the left. We'll factor this. So this will be t plus 3 times t minus 1 over t plus 3 times t minus 2. How did I know that so quickly? Remember, because we get 0 over 0, that means that for both polynomials, t plus 3 is going to be a factor, right? Because as t approached negative 3, we got 0. So that means that t minus negative 3 or t plus 3 is a factor. That's how I knew how to factor it so quickly. It's okay to factor it by hand and by brute force. It's not a big deal. Ava, you look like you have a question.
so I don't, can you explain what we mean when we factor, when we use the other way?
So if you get a number over 0, if you get a number that's not 0 over 0, so like 5 over 0 or negative 3 over 0, that's when you want to do the testing value, because number over 0 will approach positive infinity or negative infinity. But if it's a 0 over 0, that's a situation we want to use algebra to factor. So if you get 0 over 0, that's a case where we do factoring. So 0 over 0. So these cancel. We get the limit as t approaches negative 3 from the left of t minus 1 over t minus 2. And that will be negative 3 minus 1 over negative 3 minus 2, which is 4/5.
And
Yes, go ahead, Liz.
why did you use negative t is equal to negative 3? Why wouldn't you just use t to 3 is equal to 3? Right.
Because it was the limit as approaches negative 3. That, like, I don't know if that answers your question, but I
Yeah,
think
I'm just trying to see, like, when I look at a problem, how do I know if I go one way or the other? So we had learned to always just plug in if it's t approaches 2 to just plug that one in.
yes.
So when we see the little negative, then we're gonna approach.
Yes. Okay, so the good question. Good question. So that 3 minus, that's just meaning that it's going to be a one-sided limit. That minus sign has nothing to do with the actual sign of the number. So the sign of the number was negative 3. That minus sign was saying they were approaching it from the left. But since they behave very like all one-sided limits behave basically the same as normal limits, we're going to treat it like a normal limit and just factor and then see what happens.
Actually, I see it doesn't have a negative, just minus 3.
Oh no, for sure. It is small writing, so I apologize about that.
Sorry.
And then I guarantee you, if you plug it from the right-hand side, you will also get 4/5. Because it's going to be 0 over 0. It's the same calculation. If you approach it from the right-hand side, left-hand side, it's still going to do the same thing. You're going to cancel the t plus 3s You're gonna get the same thing, you plug in -3, and you're all good. Is that okay? Okay.
Like, try it, like, 0 over.
That should not occur.
Oh,
Yeah, if it's the same, like if it's the same expression inside, if it's the same function on the inside, that should never happen. It'll always give you the same thing. When it's this case, when it's 0 over 0. Okay. So if either the limit as x approaches a from the right of f of x equals plus or minus infinity, or the left-hand side equals plus or minus infinity, the key thing there is an or. And that's what the note is going to say. We say that x equals a. Remember, x equals a is an equation that says that x equals a number, but it's also can be considered a function, or like not a function, a line. X equals a is a vertical line, right? So we say that the line, I should add that. We say that the line x equals a is a vertical asymptote. And I know it looks like asymptote, but that P is silent. And it's not an asymptote, it's an asymptote. My wife always gets on my case making sure I pronunciate correctly, so I'm going to make sure that you guys pronunciate it correctly. So, a vertical asymptote. So note, you only need one of those limits to equal plus or minus infinity to have a VA, a vertical asymptote. So it just says or. That's the inclusive or, if I remember correctly. Yeah. So like we're talking cream or sugar, not we're talking cream or sugar, not super salad. So what I mean by that is, if you have one side, like if you have the limit as x approaches a from the right-hand side equals a number, but the left-hand side equals infinity, you still have a vertical asymptote there. Does that make sense? So you don't have to have both. You can just have one. You don't have to have cream and sugar in your coffee. You could have just one, though you'd be a monster. But
You could have a VA.
Hmm?
That last part is you could have a voice actor.
no, VA, vertical asymptotes. Fair. I'll put VA up here. And for representation of this note, by the way, consider these two graphs. So the following function is like they both have a vertical asymptote at x equals 1. The first function is just our standard rational equation that goes loop-de-loo on both sides. And there's your vertical asymptote at x equals 1, whereas this one is a piecewise function. For all values greater than 1, it's just the function 2. So as you approach 1 from the right, it approaches the value 2, but as you approach from the left, it approaches negative infinity. So it still has a vertical asymptote at x equals 1, despite the fact that one of the one-hand limits equals a number. All right. What time is it for? 10:41. Okay, we get out 11:20. So we gotta get a move on. Okay. So let's look at this one here. Let f of x equal x over x. Oh, did I hear a question? All right. And I'm sorry, like, well, we can do a small break in a second. So for this one, let f of x equal x over x squared minus 9 and find the limit as x approaches 3 and the limit as x approaches -7. Does f have a vertical asymptote at x equals 3? Does have one at x equals 7. So let's kind of just divide the paper in half. So the limit as x approaches 3 of f of x, or let's just write f of x as what it is, x over x squared minus 9. You'll get 3 over 0. And so because this is a regular limit, not a one-sided limit, we need to check the left and the right-hand limits because we need to check the both sides of it. So the limit as x approaches 3 from the right of x over x squared minus 9, you're gonna try x equals 3.01. You're gonna get, so let's see here, 3.01 over 3.01 squared minus 9, you get a positive number. You get 50 point something. So it's going to be positive infinity. So right off the bat, we know that this thing has a vertical asymptote there, because at least one of the one-sided limits gave me positive infinity or negative infinity. But we're asked to find the limit as well. So we'll also try and find the limit as x approaches 3 from the left of x over x squared minus 9. We're going to try x equals 2.99. So I'm just going to go back to my calculator, press back so that I can get back to it and press 2.99. 99. And you'll get negative 49.9-ish. So negative infinity. So the limit does not exist, but it does have a vertical asymptote. So the limit as x approaches 3 of x over x squared minus 9 does not exist, and f has a VA at x equals 3.
Wait, how do you know that F has a vertical asymptote at 3?
So the definition of a vertical asymptote, we had it before, like in Math 126, that if the denominator equals 0, it had a vertical asymptote. We didn't ask any questions about it. Now we have a formal way to define it, and we say that it has a vertical asymptote if either the left or the right-hand limit, one or the other or both, give you positive infinity or negative infinity. We just saw that the right-hand limit and the left-hand limits gave me infinities. That means that it has to have a vertical asymptote there. Thank you for asking for that clarification. Does that make it like, did anybody have any, like, want me to follow up or explain that in a different way? That's a very, very good question. Okay. So the limit as x approaches -7 of f of x, well, that's just going to be the limits as x approaches -7 of x over x squared minus 9. I don't foresee any problems being in this, so let's just plug it in. So -7 divided by -7 squared minus 9, you're going to get -7 over 49. Or sorry, -7 over 40. I feel like it's a personal attack on me when I'm writing a notability and I make a box and it doesn't give me a box. It's telling me, oh, that's clearly not a square. You are obviously a dumbass. Okay. Since it equaled a number, the limit equaled a number. Left and the right hand limits didn't equal, they're going to equal the same thing, right? Because if the limit exists, then the left and the right hand limits both exist and they equal that number too. So they don't equal positive or negative infinity. So no vertical asymptote, no VA at x equals -7. And just because we are on a time crunch, we're going to take a break right now, by the way. Let's take a break until 10:51. I'm going to write the answer to this one so you can take a picture and keep it in your notes. But this one is kind of an involved example that you probably won't see ever again. So we'll just have it as an experiment. But anyways, I'll write the solution up on board. So go ahead and take a break. I'm going to turn on the lights slowly, guys. There we go. Yes, Rich.
Based on the rule that if it's 3 over or like a number over 0, you're gonna get infinity, blah blah blah. Could that mean that without having to solve everything, you could say that there was a vertical asymptote?
Yeah.
So would we need to write out the whole equation on an assignment if it had like to find that, or
So if it was just asking you to find the vertical asymptote, then you could
just say that
plug in the number and just say limit as x approaches 3 from the right or whatever is equal to positive infinity. That means that has a vertical asymptote.
Okay.
So VA at this. You don't need to say like therefore, like, is that what you're
Well,
asking?
No, I'm asking because you solve both sides instead of solving both sides because you already know there's a number over zero. You
I
can say
see.
that there is a vertical asymptote that.
So yes, if you want to do that, like if it's just asking you to find the verdict, like if it's a vertical asymptote, then you can just verify by that, and that's fine enough.
Okay.
If it was asking, but this one was also asking us to find the limit. That's why we had
Oh,
to do all
okay.
that.
Okay.
But yeah, typically speaking, if it's just asking for VAs, then you can just plug it in, see if you get zero over zero, then it will.
Okay.
Yeah, good question. Good question.
Oh, my.
Another typo.
He doesn't like, he doesn't think like a different guy.
Minus two, all of it.
Oh, yeah. Say that again. I know it's wonderful.
It's kind of. It's one, I was like, no, sir, negative one, it's like. No, one, and he would not listen to me, I was like, I plugged it into the calculator. And it's negative one, and he was like, let me see. Oh, yeah, you're right. Well, arguing for the 10 minutes saying that it's negative. Oh, yes, like, oh, sir. Yeah, that's like, it's like, yeah, great question.
Because I'm multiplying every percent of the bottom and then this is x three minus x minus three.
All right. Sorry to break up the fun. We'll get back into it. So this one's kind of a niche example that has to do with the natural log and the properties of the natural logarithm. If you recall, the natural log is a function that increases very, very slowly, but it's undefined for any negative number. That's a very, very important fact about logarithms, is that you cannot have the logarithm of a negative number. So what the function looks like is looks like that. So as x approaches 0 from the right, the natural log goes to positive or to negative infinity. Oops. Those should say negative infinity. Sorry. So unlike with the other situation where we're looking at k over a number, we'd have to look at these individually and say, okay, well, x squared plus 4x minus 5. If you plug in 1, you'll get 0. Natural log of 0 does not exist. So we need to start plugging in values close to it. And you'll see that as x approaches 1 from the right, x plus 4x minus 5 goes to 0 plus. So that means the natural log is going to like, you're gonna go to negative infinity. That's just that one. So since both limits went to negative infinity, that means they're both result into vertical asymptotes. Pretty cool function. So don't worry about this. Like you can take a picture, or just jot it down right now. We'll go ahead and get started on this problem here. And by the way, I'm sorry if I'm moving forward and you haven't written it down. Just like stop by after class and you can take a picture or whatever, or you can jot it down. I'll stick around for a little bit. So this is just a fun little niche case. The limit as x approaches 0 from the left of 17x squared plus 2 over x. So one thing we can try and do is just plug it in. So this will approach what? 0. And what will this approach? 2 over 0. But it's going to be 2 over 0 from the left-hand side, right? So they're going to approach positive infinity or negative infinity. And think about it in your brain. So you're going to get 2 over negative 0.00001, right? So it's going to go to negative infinity. You can verify by plugging in the numbers in your calculator and doing the normal way, but this will go to negative infinity. So what we have is we have 0 minus infinity, and 0 minus infinity is negative infinity, right? Like that whole thing of I hate you, infinity plus 1. Infinity plus 1 is the same thing as infinity. So like that insult really doesn't matter.
Infinity squared.
Infinity squared is still infinity, actually. Infinity cubed, infinity to the 15th power, still infinity. The same size. That's actually a very, very cool area of mathematics that studies the sizes of different things, because there are different sizes of infinity. But how do we find them is a good question. I believe that area is called combinatorics. It's not my area of expertise. It's kind of a weird one for me. But anyways, so 0 minus infinity, that's just going to be infinity. However, B is an interesting case because as t approaches 0 from the right here, 2 over t squared, what will that approach? Positive infinity. And 1 over t will also, without the minus sign, will approach positive infinity. You can verify it for yourself, but like if you plug in 0.1, you get 1 over 0.1, that'll be 10. 1 over 0.01 will give you 100, and so on and so forth. So you know that it goes to positive infinity. So what we've got is we've got infinity minus infinity. What is that?
0.
Well, which one grows faster to infinity? Which, like, we don't know. We don't know. Because infinity minus infinity, you can't plug that into your calculator. 0 minus 0, you can plug that into your calculator. 5 minus 5, plug that into your calculator. There's no button on your calculator that says infinity. So how do we know what infinity minus infinity is? That's that's another type of indeterminate form.
But it's infinity minus itself, so it's forever minus forever, which is nothing.
So if you're trying to do this might be another way to explain it. If you're trying to figure out when you're trying to figure out this calculation, you can't ever start with the blue. You don't know what the infinity is. So how you're going to keep trying to find the number, and it's going to keep going bigger, and you can't get to the next number to subtract it. Does that make sense? That's
2 lines that go forever to 1.
exactly. That's a very gauge gave a great example of what this is. So think about if you've got x squared, which goes like this, versus y equals x, which goes like this. They both go to infinity. And if I took the difference of x squared minus x, the answer would be positive infinity. It wouldn't be 0 because this number would always be twice as big, or not twice as big, squared the number. So it will always blow up. Now, the way we do this is, so how do we figure it out? Cry. No. How? What should we do? Pretend it doesn't exist. It's two fractions. We hate fractions, right? We don't like fractions. So let's get rid of it. Let's combine them to give us a singular fraction. Common denominator. So the only thing that's missing is the second fraction is missing a t. So times t over t. And you get the limit as t approaches 0 from the right of 2 minus t over t squared. Right? Because then you'll get 2 over t squared minus t over t squared. So you get 2 minus t over t squared. Now let's try and plug in 0. And what do we get? Now try. You get 2 over 0, which means that it's going to be infinity or negative infinity. Yes, it's try t equals 0.01, and you'll get 2 minus 0.01 over 0.01 squared, which will equal 2 minus 0.01 over 0.01 squared. You get 19,900. So positive infinity. So this equals positive infinity. My point on this one's a new niche example that you don't see very often, but the whole point is just to say, what can you do? Always ask, like, if you're stumped on something, just start with something. It doesn't necessarily need to work. So like my thought whenever I see fractions is to say, let's try and find a common denominator. It might help, it might not, but what's the harm in trying? What's the harm in trying? And that's the case where you ask your teacher, Paul.
The whole thing that started multiply by 2 over t.
I multiply by t over t to the second fraction because the only thing that was missing, the first fraction had the full denominator. The second fraction was missing a factor of t. So it's kind of hard to see there, but I multiply by t over t on the first one.
Okay, cool.
Sorry about that. I need to zoom in again. I always forget to do that. All right. Any questions on those? So the answer would be positive infinity. And so then this brings up the so this now goes to the idea that Gage was mentioning. So imagine 0 squared, or not 0 squared, but 0.01 squared is 0.0001, whereas 0.01 is just 0.01. So the left one is going to infinity much faster. They will both go to the same infinity, but the first one is going faster. So if you're looking at the numbers, you're always going to see that there's the difference between them is going to get bigger and bigger. So one of them is going to be like if you plug in 0.01, one of them is going to be 10 billion and one of them is going to be the next one's going to be 1,000. And then if you plug in 0.0001, it's going to be like 10 trillion minus 1,000 or 2,000 or something like that. So you're just like the size of the first one's just going to dominate. And that's actually what the next part of this section is about. So instead of limits, infinite limits, so limits that give you infinity, what about limits at infinity? So do you remember horizontal asymptotes?
Yeah.
Do you guys remember the term end behavior? Okay, if you don't, it's okay. End behavior is what's happening at the end of a graph. As you just keep going out and out and out, further and further on the left or the right, what is happening to the function? What is it tending towards? Is it tending towards anything at all? So it can be useful to determine the end behavior of a function. This is found by letting the values tend to positive or negative infinity and looking for the tendency of the function values. Mathematically, we say the limit of f of x as x approaches positive or negative infinity. And we write the limit as x approaches positive infinity or negative infinity of f of x equals blah. So if you remember from you don't have to remember this, but if you remember doing any single problem in Math 126, you always ended up having only one horizontal asymptote or none, right? Every single problem, every rational function you graphed would always just have one horizontal asymptote. Well, today that's about to change. Rational functions only ever have one asymptote, but rational radicals like this can have multiple. So at first, when we're trying to figure this out, let's just test the tendency of these numbers. Now, sadly, I forgot to bring my notes on this section, so I don't have these numbers already listed out. So we're just going to have to do them by hand. So 2 times 1. I don't need to do that, but I'm going to put that in so I can plug it in later. Square root of 1 squared minus or plus 2. You get 1.15-ish. And then you plug in 10. And you get 1.98-ish. You plug in 100. And you get 1.999. We did this on the first day when we were guessing limits numerically, but those were getting closer and closer to number. Now we're making the numbers blow up. Now we're making now we're not just choosing like 3.1, 3.01, 3.0001. Now we're saying 1, 10, 100, 3,000 and seeing what number we get. So we would reasonably expect that the limit goes to 2. And so here's the thing. The reason why we're doing this here, we'll learn a few facts that will help us figure this out. But the question is, why are we doing this? How do you take the limit at infinity? You can't plug in infinity, right? So how do we figure it out? Right now, without knowing our preliminary facts, which we'll find out later, the only way we'd be able to do is just test the tendency of the y values as the x values get infinitely large. So as x approaches positive infinity, we would reasonably assume, since it kept getting closer and closer to 1.999, it'll be 2. Now, on the other hand, if you plug in -1, you will end up getting -1.15, ... -1.98, ... and then -1.999, ... So as it approaches negative infinity from the left, or not from the left, as you approach negative infinity, it will approach -2. So, yes, Paul.
Just clarify that rule about that thing in the parentheses is or negative infinity.
Yes, or negative infinity.
Okay.
Just didn't have enough space. I wanted to cram all this into one page. So if the limit as x approaches positive infinity or negative infinity of f(x) equals L, we for some number L, we say that y equals L. That line y equals L, that horizontal line is a horizontal asymptote. Or an HA. So, and then this is an important comment that I like to mention is horizontal asymptotes, they define end behavior. They're not looking at things locally. So when you're looking at a graph of a function, it could be that it crosses its horizontal asymptote a bunch of times. That's fine. You cannot cross a vertical asymptote. You can't go from one side to the other and draw a straight line. But the other thing about that is that because this is saying it's end behavior, you have two different sides, you could have two different horizontal asymptotes, as we see here. When you approach positive infinity, you get the line y equals 2. When you approach negative infinity, you get the line y equals -2. And that's very, very clear from here. So this is the graph of the function y equals 2x over the square root of x squared plus 2 is right? Yeah. So above that the limit as x approaches positive infinity of fx and equals negative, therefore there's horizontal asymptotes. So note when checking for HAs, so horizontal asymptotes, you should check both the limit as x approaches positive infinity of f of x and the limit as x approaches negative infinity of f of x. So for horizontal asymptotes, because the end behavior can be funky, you need to check both. Now that being said, if it's a rational function, if it's a rational just polynomial over polynomial, it will only have one. I guarantee it. 100% of the time, if it's just if it's polynomial over polynomial, it will only have one. It's when you have a polynomial over radical or a radical over polynomial or something like that, some weird stuff, that's when you really want to be careful and actually look for it. So if it's just a polynomial over polynomial, it's probably only going to have one, it will only have one horizontal asymptote, and you don't need to check both. So as another example of this situation where you could have some interesting things, we have f of t equals e to the t if t is less than 0, and t squared if t is greater than or equal to 0. So if you want to graph this function, let's just assume every tick mark is 1. Then for t is less than 0, at 0, e of t is 1. E of 0 is 1. So this is part 1 and this is part 2. So piece 1 starts at 1 and then just decreases indefinitely. Whereas if you're greater than or equal to 0, your t squared, that's parabola centered to the origin, and it just grows infinitely. It looks like this. So the limit as t approaches negative infinity of f of t equals what? It approaches 0. That line keeps getting smaller and smaller and smaller. So that'll equal 0. And the limit as t approaches positive infinity of f of t, what do you think that's going to be equal to? It keeps going, like as you move further and further out to the right, the y values just keep getting bigger and bigger and bigger and bigger. So as the y value, as the x values went bigger and bigger, the y values tended towards larger and larger and larger numbers and never stopping. So this one will be positive infinity. Even so, even though the limit as t approached positive infinity gave us positive infinity, we still had one of the limits at infinity being equal to a number. So it still has the HA at y equals 0. It's just that only one side tends towards that number. It's only the left side. The right-hand side just blows up. But it's still a horizontal asymptote because the y values tended towards 0 for at least one direction of infinity. Look at the notes here for just a second. Okay. So we're getting low on time, but we should be able to get most of this. So this is a fun one. This took me forever to graph because I had to make each thing, like this is a piecewise function. Creating that squiggly line was a nightmare. I'll tell you, it involved e to the x and several trig functions to make it do that. It's very fun. It's very fun messing around with that. Desmos is a very fun thing to do once you learn how to do it properly. With like cardioids and stuff like that. Yeah, it's fun. I like how you can use polar coordinates in it. It's super cool. Okay, so just so we're clear, you notice how it just keeps getting like the slopes keep getting smaller and smaller. We're going to assume like it's going to basically level off at that number, which is right in the middle. So the limit as x approaches positive infinity. Let's highlight that in red. As x goes this way forever, what do the y values tend towards? 2. The y values keep tending towards 2. Whereas as you approach negative infinity, yep, it's hard to see on my graph. I promise, like like this was this was when I was still not having my graphs look perfect. So on an exam or on a quiz, if there's a graphing problem, I will make sure it's very, very explicit what the numbers are, so it's easy, like it's easier to tell. But yes, this tends towards -1. How about as x approaches 1? DNE, very, very good. Because as you approach it from the left, it approaches 1, and as you approach it from the right, it approaches 3. The limit as x approaches -3 from the left. Positive infinity. Let's see why that is. So as you approach -3 from the left, the y values get closer and closer to positive infinity. But as you approach it from the right, you go down to -1. So what are the asymptotes? So we have VAs and we have HAs, right? So VAs. Do I have any VAs? Do I have any vertical asymptotes? Just at -3. X equals -3. That's the only one that has a number that goes to, oh yeah, I see what you're saying. Yeah. And then for horizontal asymptotes, we have 2. We have one that's tending towards 2. So for HAs, and because horizontal asymptotes are equations of lines, we have y equals 2 and y equals -1. I don't know why I boxed that. So, fun problem. Imagine all the questions we could ask about this. So much fun, so much room for activities, right? So many good problems that could be asked. And that's why you'll probably see on every single one of your exams at least one graphing problem. Just letting you know. Graphing problems are really fun.
It's
Oh.
because it gives me a visual.
Yeah, I love them. They're like, there's so much you can gather from a graph. Okay, that's great if you have the picture, but trying to tend the number, like trying to figure out like just by plugging in numbers seems a little bit tedious to me. It seems like that's not the best way to go about doing things, right? Well, how do we find them analytically? Well, we need a couple facts. And the first one is that for a polynomial, we only need to look at its highest degree term for x tending to plus or minus infinity. None of the other terms matter. When you're talking locally, when you're talking about the limit as x approaches 5 or x approaches 10, all the factors matter. But if you're talking about end behavior, you're talking about infinitely big numbers, right? Like things that we can't even imagine how large they are. All the other stuff does not matter. No matter how big the other stuff is, the thing just gets dominated by the highest degree term. So what I mean by that is at infinity, as x goes to plus or minus infinity, the polynomial gets dominated by highest degree term. So we're going to do a problem showing you what I mean, and then I'm going to explain why. So that's an important fact for polynomials. And you're looking at like, and this is only for limits at infinity. So limit as x approaches positive infinity or negative infinity. None of the other factors matter. It's just the highest degree term. So for this one here, the limit, wrong color. The limit as x approaches positive infinity of p of x, which is x to the 5th minus 2,317 x to the 4th minus 1240. That 2,317 x to the 4th, despite being a very, very big number, does not matter. This is just the limit as x approaches positive infinity of x to the 5th. And what will that tend towards as x goes to positive infinity? You get positive infinity to the 5th power, so that's just going to be infinity to the 5th. That'll be infinity. And then if you look at the limit as x approaches negative infinity of x to the 5th minus 2,317 x to the 4th minus 1240, that's just going to be, once again, the limit as x approaches negative infinity of x to the 5th. But this time, you're approaching negative infinity, right? So you've got negative infinity to the 5th power. And we know that odd powers keep the same sign, right? A negative to an odd power stays negative. A negative to an even power stays positive. All right, so this will go to negative infinity. And just because I'm thinking it, which means maybe one of you guys is thinking it, you might be saying, so the limit doesn't exist. Remember, these are two different limits. These aren't going to the same thing. This is not like checking the left and the right hand limits of a number. This is checking two different completely opposite spectrums of the function. And that kind of makes sense if you think about a polynomial x to the fifth. Remember, x to the fifth polynomials kind of look like this. So as you approach negative infinity, it goes down. As you approach positive infinity, it goes up, right? Now, why is that true? Why is that true? It's because we're talking about end behavior. We're talking about the largest numbers you can imagine. 1 billion to the fifth power is bigger than 1 billion to the fourth power by a factor of 1 billion. It is 1 billion times bigger than it. It's that much bigger. So, and that's just 1 billion. We're talking like, what about one Googleplex or one like 10 times 5 hella what's the hella measurements? 10 to the 27th, right? Good old Californians with that that measurement. Either way, we're talking about big numbers. So the smaller stuff doesn't change. Yeah, it's a big number, but not in comparison to the other thing. It's a much like the highest degree thing is a bigger fish, as Qui-Gon Jinn would always say. So preliminary fact number 2, we'll say this. Okay, so we'll just write the preliminary fact number 2, that the for any a greater than 0, the limit as x approaches as x approaches plus or minus infinity of 1 over x to the a equals 0. The limit as x approaches positive infinity or negative infinity for anything 1 over x to the something is just 0. For any a value. Oh, that doesn't look like anything you can read. A greater than 0. For any number greater than 0, 1 over x to the a will go to 0. Because even if it's negative 5 billion, 1 divided by negative 5 billion is still 0. It's very like it's tending towards 0 from the left, but its actual limit will be 0. And we'll use that, and then we'll figure out how to calculate limits at infinity analytically. Okay, guys? That's what we'll leave off for today. If you have any questions, feel free to email me. Otherwise, you guys have a great rest of your weekend.
Negative infinity or is it positive negative a?
Positive and negative infinity. Let me write that better. All right, guys, have a great rest of your day and a great weekend. If you have any questions, feel free to come up. Otherwise, I'll see you then. I'm going to turn on the lights. Not next Wednesday, the following Wednesday, right? Yeah, not next Wednesday, following Wednesday. So 2 weeks from now, 2 weeks from today.
What's 2 weeks from today?
The 15th. Yeah, of course.
I was
And Raheem, right? Yeah, what's up?
trying the homework question from unit 1.2.
Okay.
So I tried it, but around this area, it kind of got blurry for me.
Okay.
So I was just testing different things to see how it works. So this like from here to here to this.
Okay. Well, let's see here. No. I want to verify something before I say what's going on here. Okay. So here's the issue. So you're right in finding a common denominator, but the thing is, this thing already has a factor of k, so it's not missing anything. This is the only thing that's missing something. So you should multiply this by k. Let me write it down so you can see what I mean. So you've got 1 over k minus 1 over k times k plus 3. Does that make sense? This is k squared, right? K squared plus 3k. So this term already has a factor of k in it. So you don't need to multiply it by anything. All you need to do is just get this thing to have the common denominator. So you only need to multiply this by k plus 3 over k plus 3. Does that make sense?
Yes, yeah.
So that'll fix everything.
So just, okay,
And so that should give you k plus 2 over, can I see it again? Should get k plus 2. Oh no, that's a 3, not a 1. So when you do that, you should get k plus 3 minus 3. So it'd just be a k up top and then a k times k plus 3. And then those cancel.
okay.
Is that cool?
Because I was doing both sides by the. Okay.
Yeah, that's gonna be the issue. So
So how do you know when to just do one side?
so one of the things there, this is, I'm still recording.